right, so good afternoon, everybody. My name is Jesse, and I am with Exploring by the Seat of Your Pants. I know we've got a lot of familiar faces today, but if you are new to our broadcast, we are all about bringing conservation, adventure, and science into classrooms around the world. Now, we specialize in field work. We've been to every continent. We've been to 95 countries. We've blasted through jungles on islands and oceans and more. And today we're going to throw all that out the window. We're doing a completely different kind of program, and I am very excited for our speaker today. So we've done two programs with John Donohue before, and he is at the Institute for Quantum Computing at the University of Waterloo. The University of Waterloo is one of the world's leading research, amazing organizations, institutions working to share a passion for science with the public like we're doing today. And so John's going to walk us through a little bit more about the quantum realm. It's fascinating. What is it? What's going on? Is it related to Avengers Endgame? I don't know. We're going to do some light experiments together, literally with some light. I'm very excited about this. We've had the chance to do this before, and it was one of my very favorite unique programs we've ever had on the broadcast. And so, without further ado, I will stop talking and turn it over to John to blow your minds. Thank you so much for joining us today, John, and take us away.
It is my pleasure. Thank you so much, Jesse, for the kind introduction. My name is John Donohue. I'm from the Institute for Quantum Computing at the University of Waterloo, and today we're going to be doing some experiments related to quantum mechanics. So, before we dive into that, just a little bit about myself. So, I'm from the University of Waterloo, and I did actually my graduate studies at the University of Waterloo after studying physics at the University of Windsor. Uh, what I got into physics. I wasn't really sure what I would do with it as a career per se, but I got into it because I really liked playing around with the mathematics. I really liked diving into some of those details, messing around with it, learning how different maths could be used to describe the world around us, and thought I really wanted to be a theoretical physicist. But eventually, I started getting into research in university. I started entering things called co-op programs, which allowed me to try different experiences along the way, and realized I really liked playing with my hands. I really liked getting involved with some of these experiments. And in particular, I worked on experiments related to light and optics. So, how we understand quantum physics by playing around with lasers, playing around with special special crystals and special detectors to really understand the universe. What I really liked about this is that you could actually build an experiment very, very small, and use that to understand how the universe works. That's what physics really is we're building experiments and trying to understand experiments and understand the rules of the universe. In particular, today what we're going to be talking about is the rules of quantum mechanics. So this demonstration is timed with World Quantum Day. So World Quantum Day was celebrated on April 14th, and it is a day for the community around the world working in quantum research to come together and celebrate this theory that has been with us for over a century now. So we've understood the world of quantum mechanics for a very long time, and we've used it to build many really interesting technologies. Things like MRI scans, things like lasers, and we're still developing our understanding of quantum mechanics to build things like quantum computing and build things like new kinds of sensing technologies, which we'll talk a little bit about at the end. But if you're interested in looking up more, there's tons of other stuff you can dive into about quantum mechanics. You can find more from us at iqc.ca, and you can find more from around the world at worldquantumday.org. But the first thing we should probably do is talk a little bit about just what quantum mechanics is. So, when most people hear the word quantum mechanics, they probably picture something from pop culture like Ant-Man. So, if you haven't seen Ant-Man or if it's been a while since you've watched it, what happens in Ant-Man is a superhero who can control his size. So, based on the powers of his supersuit, he can make himself really, really, really big or really, really, really small. Now, when he goes really, really small and keeps going and keeps going and keeps going, eventually he, gets as small as a mouse, as small as an ant, and then eventually gets as small as an atom or as small as a molecule. And he keeps going even smaller and smaller than that. And eventually he enters what's called the quantum realm. And this is a realm where he can harness infinite amounts of energy and where basically the rules of the universe don't seem to apply anymore. And this is a really cool way to visualize it, but also not at all how quantum mechanics works. So if we take Ant-Man for granted, then we think about quantum mechanics as something that has no rules, when the reality is that quantum mechanics is something that has many rules, and that those rules are well understood by scientists in the field. So, quantum mechanics is really the rule book of physics that we need to describe the submicroscopic universe. So, it's the rule book that things like atoms and electrons and photons and molecules have to follow. Now, just because there are rules does not mean those rules necessarily make immediate sense to us. So, for example, in the quantum world, energy is quantized, not continuous. That means that energy can only exist in kind of steps of a ladder instead of any possible level of energy, but it does obey rules. We call some of these rules the superposition principle and the Schrodinger equation. We can model them very precisely mathematically. Quantum mechanics is, in a sense, the most precise theory that mankind has devised to date. It just sometimes conflicts with our natural intuition. And that's what I'd like to talk about today. I'm going to talk about two ways that quantum mechanics conflicts with our natural intuition, and we're going to do a couple experiments that show some of the results of that conflict. And the first thing I'd like to talk about is something called wave particle duality. So, whether we think of something as a particle or a wave depends on its properties. Usually, when we think about objects in the universe, we think about them as particles or waves. We think about them as one or the other. If I give you a tennis ball, you're probably going to say, that's a particle. If you listen to an audio signal, a sound, you would think, okay, that you can believe that that's a wave. So certain properties that each have, well, we have particles, they tend to only exist at one place, whereas a sound or other kind of wave can be spread over a large amount of space. Particles have properties that we can look at, like their mass or weight or their volume, how big they are. A wave has different kinds of properties: a wavelength, how long the wave is; a frequency, how fast or high pitched the wave is. When two particles collide, they tend to go like billiard balls and have kinetic collisions. They bounce off of each other. When waves collide, we see something called wave interference. And just generally speaking, we think of particles as something that we can count. If you give me three tennis balls, I can say I have three tennis balls. Whereas a wave might be something that's a bit more continuous. I can turn a sound wave to high volume, low volume, or anywhere in between. It wouldn't make sense for me to say I have three levels of sound, because I could also have 3.1 or 3.2 or 2.9. It's really a continuous range that I can tune it there. So when we think about particles, yeah, we're thinking about like cannonballs. We think about waves, we might be thinking about sound waves or ocean waves, for example. So let's dive into one of these phenomena in particular, this idea of wave interference. When two waves meet, do they bounce off each other or does something else happen? Okay. So let's see what we can do with water waves. So if I drop a pebble in a pond, and I'm sure all of you have done this, you throw a rock in a pond and you find that it makes these circular waves that go out from the center. Okay. The wave keeps spreading and spreading and spreading. We end up with this very, very large circular ripple pattern. Now, what happens if I instead take two waves, take two rocks, and throw them into the same pond? The waves from one of the two rocks is going to merge with the waves from the other rock. And we see some interesting effects. So, this picture shows it just in case this experiment doesn't work, but let's see if we can see it in real life. So, I'm bringing myself up on the camera here. Hey, everyone. Okay. Yeah, you can see me okay? So, yeah, as mentioned, when we drop a rock in a pond, we see that wave spread out. So, what we have here is something called a ripple tank. And inside the ripple tank, we have some water and we have uh, something that's going to mimic those two rocks, right? We have let's call it a prong, let's call it a dipper, and it has two sides to it. And when I turn on this button, they start vibrating. So I'm going to take off my headset for a sec so you can hear the vibrations. Hopefully you got a chance to hear that through the microphone there. Okay, now we can't really see anything going on right now. So what I'm going to do is I'm going to turn on a strobe light. And when I turn on this strobe light, what's going to happen is it's going to show us the waves. Okay, so I'm going to turn off the waves for a second there. And I'm just going to turn on the strobe light. Now we can see the light through the water there. And what's going to happen is when the waves are present, it's going to cause the light to bend almost like a lens, and we're going to be able to see where the ripples are high and where the ripples are low. It's going to blind the camera though, so I'm going to put a little bit of a screen over top of there and turn the waves back on now. Okay, now we should be able to see those waves. So this is looking at the waves coming out as the prongs, as the dipper is bouncing back and forth. We see one circular wave coming out right here and one circular wave coming out right here. And now it's a little tricky to see, but we see that there are certain lines, right, where the wave is very intense. We see this like big oscillation, meaning that we see very, very bright parts and very, very dark parts. Let me move this camera just a little bit this way. So like right here, for example, you see the wave moving out and it's got these very, very bright and dark patches. But if I move just a little bit over this way to right here, we see there's basically no patches at all. It's almost like a line where nothing happens. And then we move a little further over and we see this line where once again it's big, very bright patches and dark patches. And then we move over again and we see once again nothing really. We see it's almost like there's no wave there whatsoever. So these lines where there's a very, very strong wave and these lines where there's basically no wave whatsoever. Okay, so we're going to look at that one more time. This is something that we call interference. So what happens is we have waves coming from the source over here, from this dipper, and we have waves coming from this dipper over here. Now the waves, they kind of, they're waves, they go up and down, they oscillate is the word we say there. And when they meet, if they meet where they're both going up and down at the same place, so when this one's high, this one's also high, they're going to meet and merge into an even bigger wave. We call this constructive interference. But if we say make it so that they're at slightly different distances away from each other, so the waves have a little bit longer or a little bit shorter to travel, then they might get to the point where when one wave is very high, the other wave is very low. When one's at a peak, the other's at a valley or a trough. And now when these two waves meet, what they're going to do is the peak is going to cancel out the trough, they're going to cancel each other out, and we get something called destructive interference. So if we go back to this setup over here, these lines where we see the very, very strong wave, that's constructive interference. And where we see no wave at all, that's our destructive interference. Okay, and we see that if you weren't able to see that too well on the camera picture, you see it very clearly here. So this is our constructive interference here, where we see the bright and dark patches very clearly. And this is our destructive interference here, where they cancel each other out. Okay. So I just tried to mimic this with my hands, but if you like looking at things in terms of waves instead, when the peaks and the peaks meet up, they form an even bigger peak. When the peaks and the valleys meet up, they cancel each other out, and we see this destructive interference. So whenever two waves meet, they create interference. This is indeed one of our telltale signs that we're dealing with a wave, is if we can see this interference. So a long time ago, people were arguing about what light was. So we knew that waves, like sound waves and water waves, would have this kind of interference phenomenon. But what about light? So the idea, the one that proved that light indeed is a wave in the same way that sound is a wave and that waves in water are waves, was something called the double slit experiment. In this experiment, Thomas Young, what he did was he took a beam of light and shined it through two narrow openings that are called slits. Now the light could expand through one slit or expand through the other slit. And when it did, the light from one slit would meet and potentially interfere with the light from the other slit, just in the same way that the water waves from one dipper interfered with the water waves from the other dipper. Now, then, if light behaved like a wave, we would expect to see some regions where we get constructive interference, the light gets even brighter, and some cases where we see destructive interference, the light gets dimmer. And indeed, when you do this experiment, this is actually a very difficult experiment to do in the 1800s and a very easy experiment to do today now that we have laser pointers that we can get from the dollar store, is we can see these regions of constructive and destructive interference. I'd like to go back to the camera. So I'm going to get rid of the water waves for now, and we're going to see another way that we can see this interference with light. Just hide the water waves carefully without spilling too much along the way. And we're going to use something called an interferometer. Okay, so in order to see interference, just like with the water waves, we need light that can come from one of two different sources. So in the water wave experiment, we had the water wave coming from this dipper or from this dipper. In the double slit experiment, we had the light going through this narrow opening or this narrow opening that spread into each other. We're going to use something called an interferometer, and that's where we start with a laser. So we have our laser right here, and it's going to emit green laser light, and it's going to hit something called a beam splitter. So this right here, this black line here, is what we call a beam splitter. And what happens at a beam splitter is you can think about it like it's almost a mirror, but not quite. So when you have a mirror, all the light gets reflected. If you have a piece of glass, all the light goes straight through. For a beam splitter, half the light is going to go straight through, and half of the light is going to be reflected. So then we're just going to redirect them using mirrors. So these are just regular old mirrors here. And then we're going to have these two paths meet at another beam splitter. Okay? So if we just had one beam of light, let's say we blocked this one right here, then the light would hit the second beam splitter and split in half again. If we were to block the other one, we would see the exact same thing. But if we let both paths meet at this second beam splitter right here, what can happen is, well, some of the light came from this way, some of the light came from this way, depending on whether or not the waves are going together or going opposite, we should be able to see some interference. So this is what it looks like on a sketch. In real life, it looks a little more something like this. It's going to turn on the lamp for a sec because it's hard to see without it. So we have our laser beam right up here, and we have our beam splitters here, and two mirrors right here. So I'm going to turn on the laser, and you can see the laser beam a little bit. It's not very clear because the thing about lasers is that, well, they just travel through space. We only see them when they hit the ground, like right there. So let's give them something to interfere with. I have some spray fog right here used in photography often, and let's see what happens when we spray and see where the laser beam is going. We're going to give the laser something to scatter off of. We see that indeed the light is going off this first beam splitter, hitting this mirror, merging at the second beam splitter, and both paths come together. Now, eventually I'm not going to be able to breathe, so unfortunately I have to stop spraying it at this point and use a little air blower to get rid of some of that dust. Okay, so that's the experiment we're going to do. Now this one, unfortunately, because I just sprayed it with the fog, is now covered in gunk, so it's not going to work to show interference. But I have a fancier one of the exact same thing that we can use to see that interference. If I can just, sorry, my headphone's a little tangled. 1 second. There we go, that should be better. Okay, so this is our bigger interferometer. Same exact thing going on, just a little bit more expensive, a little bit fancier. I'm going to turn on my laser, and I'm going to block one of the two paths like that. Okay, so we see we have our laser back here, our mirrors and everything here, and we're looking at where the light comes out over here. And if I block one path with my hand, we see the two dots corresponding to the light being split at the end. But if I let both paths go at the same time, we see these bands right here, right? So if I put my hand in one half of the path, those bands go away. If I put them in the other half, the bands go away. But if I leave both paths open at the same time, the light from one path interferes with the light from the other path. Sometimes they interfere in phase and we get an even bigger wave. That's those bright bands right here. And sometimes they meet out of phase. So one's a little higher while the other's lower. And we see these dark bands here. So this is what we call a Mach-Zehnder interferometer. We split the light into two paths, we merge them back together, we use that to see interference. This effect is really at the core of quantum mechanics. It's also at the core of a lot of sensing technologies. For example, if you really like physics and you heard about the LIGO interferometer, interferometric gravitational wave observatory, what they used to measure those gravitational waves a few years ago, it's still running today. They were using a system very, very similar to this. And the idea there is, okay, let's look back at our waves again. We see these bands of bright and dark. Now, say I'm a gravitational wave. What a gravitational wave does is it stretches space in a very specific direction. And I can mimic that in this setup by applying pressure to the board, which is going to bend it in such a way that one path gets a little bit longer than the other path. And what happens is I'm just applying a little bit of pressure just with my thumbs. This is a solid steel board, so it's really a very, very slight bend. But just the pressure I'm able to apply with my thumbs is enough that those bands, hopefully that frame rate is good enough that you're able to see those bands moving along. I'll do it very slowly just to make sure you can see it. Is that those bands of light and dark move around. And now if I'm running the LIGO observatory and I'm able to see those bands move slightly where there was constructive interference turn to destructive interference, I can use that to measure whether or not there was a gravitational wave present or not. So they use a much, much bigger interferometer. Actually, the arms in this interferometer, like how one path versus the other, it's maybe half of a meter. In the LIGO observatory, it's a couple kilometers, so much, much bigger. But the same basic principle as is at play here. Okay, I'm going to switch back to the slides for a second. Okay. So, one of the things about light that really astounded people in the early 1900s is that light, after Thomas Young's double slit experiment, things like these interference experiments, we were very sure that light is a wave. But there was evidence brought up by Max Planck that light actually might be made up of particles that we call photons. Okay? Now, when I say particles here, remember that a particle is something that has properties that we associate with particles. It has mass, volume. In particular, what Max Planck showed is that we can actually count light. So at the quantum level, I don't have something like a wave where it can be a little wave, a medium wave, or a big wave, or anything in between. I actually have either 0 units of light, or 1 unit of light, or 2 units of light. I never have half of a unit of light or pi units of light. Max Planck called these units photons. So light, we know it behaves like a wave. We've seen these interference experiments, but we can also count it. So something a little funny seems to be going on there. And indeed, we can actually do experiments like that double slit experiment, one photon at a time. So this is data taken at the Institute for Quantum Computing at the University of Waterloo. Each dot here corresponds to one single photon being measured in an experiment. So I'll let it run from the start. It doesn't look like much at the very, very start, right? We just see dots randomly here or there. Each of these photons was passed through a double slit experiment. But if we let this keep going and going and going, we eventually see these bands where we see constructive interference and destructive interference. So even though there's only one photon at a time, even though we only measure one photon at a time, we still see constructive and destructive interference. This is what we call wave particle duality. We cannot describe light as if it is a wave or as if it is a particle. It has some properties, like interference, that we associate with waves, and others, like being countable, that we associate with particles. But the truth is, the idea of waves and particles is something we have to give up when discussing photons and light. It's not something that can be applied straightforwardly. We can sometimes sum this up with what we call our two golden rules of quantum mechanics. So quantum mechanics can be a very mathematically complicated theory if we want to get into the details of it, but the basics of it are really encapsulated by these two rules. Rule number one is superposition. A particle can behave as if it is both here and there. Basically, we can have something where the photon behaves as if it is both in the right slit and the left slit, in the top path and the bottom path. Essentially, it can behave like a wave. But when we ask it where it is, when we put in a measurement that asks the photon, are you here or there, it's going to be found in one or the other. So things have to make decisions and end up in a specific place, like particles. But before we ask them questions, they can be in different places, spread out, like waves. Okay. So One of the natural questions that scientists asked after discovering that light behaved like a particle and a wave was, well, we thought light was a wave and it ended up behaving like a particle. Does something that we think of as a particle behave like a wave in certain circumstances? And indeed, if we look at things like atoms and molecules and electrons, we can actually see their wave behavior. So that double slit experiment I showed you with photons, here's something that looks very similar, but it's done with individual electrons. Electrons are the charged particles that orbit atoms. They're what move around in conductors to make electrical current, and they have properties like mass. We know the mass of an electron. It's very small, but it has a weight to it. And we found in these experiments that we can see wave-like interference using these particles. Indeed, this is an experiment done in Vienna in 1999 where they showed interference using a buckyball, a large a large molecule made of 60 carbon atoms. Now, to show that ourselves, we're going to look at something called an electron diffraction tube. This is going to work very similar to the double slit experiment, but instead of using light, we're going to use electrons. So we have a tube that looks something like this. I'll show you it in real life in a second. And what's going on inside this bulb is we have a cathode, so something we're going to heat up very, very hot, and then we're going to apply a strong voltage to it to kind of rip the electrons, rip the current away from it. Those electrons are going to hit a metal sheet that is going to act kind of like a double slit, although a little bit circular. And then every time the electron hits the edge of the bulb, it's going to uh, annihilate such that it forms a green glow. So every time an electron hits the bulb, we're going to see a green glow. Now we're going to be sending a lot of electrons at once, so we're going to see just a large green blur instead of electrons one at a time. But let's take a look at it and see what we're dealing with. So I'm just going to move the interferometer out of here real quick. And bring up the electron diffraction tube right here. Okay, so this is our electron diffraction tube. It's got a voltage source that we're going to use back here. All right, now what's the best way to frame this? Here we go. That should work. Make sure all the plugs are solid and then turn it on. Okay, so right now there's no voltage, and as I apply a little bit more voltage, we start seeing that green glow, right? And that green glow is electrons coming from the back filament here. Let me see. I'm going to try to move the camera a bit so you can see the hot glow of the filament back there. That red light, that's the hot glow of the filament. That's what's liberating electrons and allowing them to travel through here. We then have a large field right here that's accelerating the electrons. They hit this screen. Every time they hit the screen, it glows fluorescent green. Now, this green dot, I'm going to keep turning up the voltage, and that's going to speed the electrons up more and more and more. And now we see that glow get brighter and brighter and brighter. Now, and just to convince you, because you might be thinking, wait a minute, no, there's no electrons there. He's lying to me. And what we're actually doing is shining a laser beam here. What I have here is just a bar magnet. So this is a very, very, very strong magnet, but it's a magnet. Now, if I have a laser pointer, that shouldn't care about magnetic fields, right? I can't hold a fridge magnet and use it to bend a beam of light. But electrons that move are actually emitting a small magnetic field, and they will respond to magnetic fields. Something through the laws of physics, something called Maxwell's equations. Moving charges respond to magnetic fields. So if I take this magnet and hold it back here, we see that I can move that dot around. So this isn't something uncharged like light. There is some moving charges happening here because they're responding to this magnetic field. Okay? So I'm going to put that up to max power now. And right now I'm blinding the camera. So I'm going to put the screen back up just to dim the image so you can see what's going on here a bit clearer. Now we look at what's going on here, and we see that not only are we getting a brighter glow, we're also starting to see something else. Oh, sorry, you're seeing a little bit of glare there. Let me see if I can reduce that. Yeah. So we see that it's brightest right here, and then it gets a little darker, and then it gets brighter again. Then it gets a little darker again, then it gets brighter again. What we're actually seeing is that same constructive and destructive interference, but instead of seeing it with light or sound waves or water waves, we're seeing it with particles. We're seeing it with electrons. Okay, so I'll show that one more time in case you missed it on the first one, but we see that, hopefully you see that little dip in intensity right there. That is evidence of electrons behaving like waves, which is really cool. Okay, and just in case you weren't able to see too clearly on the camera, here's a still image of that. Okay, and just hide that before it overheats itself. So that was all about wave particle duality, and that was the first thing we were talking about, the first way that quantum physics differs from classical everyday physics. So the next way I'd like to talk about is how physics can be different, and especially how quantum physics can enter when we start dealing with different temperatures. And this section is titled Cooler Than Being Cool. Okay, so what is temperature? So when we think about temperature in our day-to-day life, we think about, usually the centigrade Celsius scale, where we think about certain things happening at different temperatures. Temperature is what we feel when we go outside, either hot or cold. At certain temperatures, special things happening. So at 0 degrees Celsius, for example, ice melts. At 100 degrees Celsius, water boils. These are two things that we note that happen at a very specific temperature. Now, what is temperature at the molecular level, though? At the molecular level, temperature is a thermal energy. So when water cools down to 0 degrees Celsius, it becomes a solid. The water atoms, the H2O molecules in there, they stop moving as much. They become much more rigid and form a solid. At 100 degrees Celsius, the water molecules stop being bound together as a liquid and become free as a gas, as vapor. And in the middle, even if I take water and cool it down from 50 degrees Celsius to 20 degrees Celsius, what's happening is those water molecules have less kinetic energy, they're moving around less, they're vibrating less. So as we cool things down, the molecules at the atomic level start and stop moving as much. Okay. This actually relates to pressure. So let's take a look at a balloon, for example. We have air molecules inside the balloon represented as these red dots. As the temperature increases, the energy, the kinetic energy of those molecules increases. The pressure increases because pressure is just the molecules bouncing against the edges of the balloon and the balloon expands. Okay. So as the temperature increases, the molecules bounce and bounce and bounce around even more. They hit the edge of the balloon and they increase the size of the balloon. Okay. This is why if you've ever, heard people say that when you have a car, you shouldn't inflate the tires too much as it turns into summer. That's because if you do it too much, the tires are going to increase a little bit in size and could pop. It's possible. I've never seen it happen, but I've been scared about this for ages. On the flip side, if I take a balloon and I cool it down, the heat is going to decrease, the temperature decreases, the kinetic energy of those air molecules decreases, the pressure that they exert against the walls of the balloon decreases, and the balloon deflates. Okay? Now, temperature can go to much more extreme scales than 0 to 100. If we heat things up to, say, 327 degrees Celsius, things that we think about as definitely solids can become liquids. So that's the temperature at which lead melts into liquid lead. On the other side, if we go really, really cold, things that we only think about as gases can actually become liquids. So, at negative 196 degrees Celsius, nitrogen liquefies. Nitrogen is the most common element in air. It is always a gas in the ways that we interact with day to day. But if we cool it down to negative 196 degrees Celsius, it actually becomes a liquid. Let's see what happens when we get to that level. So for this part, I'm going to have to put on some gloves for safety because we have with us a bunch of liquid nitrogen. Now, liquid nitrogen, as mentioned, is negative 196 degrees Celsius. That is very, very cold. If you get that in your hand, that's going to give you frostbite very quickly. So before I handle it, I must put on my big gloves. And now I'm going to go grab the liquid nitrogen. Okay. So this right here, come on, there we go. It's bucket up nitrogen. As we kind of like move it around, we see that it's essentially converting to gas relatively quickly. There's a good amount in here, so it's keeping itself cold. But as soon as it interacts with the air, it wants to turn into gas, and it also wants to freeze the water vapor in the air to condense into there as well. So this is negative 196 degrees Celsius. And now one of the things I like to think is that this is kind of a test. Based on what we saw about what temperature is earlier. Oh, of course, all the quantum stuff is easy. The difficult part is actually inflating balloons. This is the tough job. So, okay, I've got a big long balloon. Just going to tie that up real quick. Nothing fancy. I pumped it in front of you. I'm not cheating. uh, Yeah, I got the electron diffraction tube to work no problem, and it's getting the balloon to tie itself. That ends up being the tricky bit.
Always a challenge in every one of our broadcasts, actually.
There we go. Oh, no! It's gone.
You're giving us comic gold here, John. This is
It's
beautiful.
okay.
Yeah.
Thankfully, I got a backup, so we're good. All right, so I got a balloon. It's roughly as tall as I am, maybe a little bit shorter. Can I fit it into this little box? I could maybe try to jam it in there, but I want to try to do it just like this. And let's see what happens there. So I got to get my gloves back on for this. Now, right now, remember, what is keeping the balloon active here is that the air molecules inside the balloon are bouncing against the edges, keeping it inflated, applying that pressure to it. If I cool that balloon down to, say, negative 196 degrees Celsius, I find that I'm just able to pop it right in there, no problem. Now you might be thinking, okay, obviously he's lying to me again. He didn't fit the balloon in there. He popped the balloon. He deflated it, and that's why it fit in there. In which case, when I take it out, it should remain deflated. So there's a small chance it pops here, but we see that it automatically reinflates itself. I get the feeling it's actually going to pop right there. There's a little bit of tension right there. That's not perfect. No, it looks like it's going to make it. It made it. All right, and we're right back to our full balloon. As it cools down, the air molecules inside the balloon cool down, and the balloon effectively deflates. There's less pressure against it. Once it heats back up to room temperature, though, it's back to being a balloon. Let's see that one more time with hopefully an easier balloon to manage.
This is your moment of truth. I believe
Here
in
we
you.
go, here we go, here we go. There we go, and we're good. Okay, so this balloon does not quite fit inside, but if we push it, it's now bottom touching the liquid nitrogen. We can hear it boil a bit too. Let's get the mic a little close. Might be hard to pick up there. And eventually it goes in there.
Balloon doesn't know what hit it.
Now if we take it back out, it'll reinflate itself rather quickly. Okay. So this isn't the only thing that changes when temperature decreases. So what I have here is a light bulb. Make sure it turns on. It's not very bright, as we can see, though. Now, that's because what we've done is we've hooked the light bulb up to this long coil. So instead of being a short circuit that goes, from the light bulb to the battery, we make it first go through this very, very long coil of copper. Copper is what we call a conductor. Electricity does flow through copper, but if we put that much copper in there, it's going to add resistance and reduce the current, resulting in a less bright light bulb. But if we cool the copper down to, say, negative 196 degrees Celsius, we see that light get very bright very quickly. Now then, notice that it's boiling, right? That's because the object was originally hot, and when we put it in there, it started rapidly boiling like nitrogen. It's like we put a very, very hot poker in there. I'll put my mics closer so you can hear it. All right, so that's that boiling as it cools down, as everything comes to thermal equilibrium. Once the boiling stops, we know we're at thermal equilibrium, and we see that this light has gotten much, much brighter. Now, as we take it out, it will eventually cool down, but it's going to take a while because that's able to hold that temperature for quite a while. Now, it's not just that things get less resistive, actually. So in that case, what we saw was that the copper lost resistivity. It allowed the electrons to flow through it much more easily. As we cool objects down, their conductivity increases. They conduct electricity more easily. Some objects get an even more special thing called superconductivity, where when they hit a certain temperature, they actually reach zero resistance. Electrons flow through them as if there was nothing in the way whatsoever. So I'm going to grab a piece of superconductor right now. So these two pucks are made of a superconducting material called YbCO, yttrium barium copper oxide. I'm going to pop them into the liquid nitrogen for a second. Here's a broken one just so you can see what's on the inside. It's like these little strips of metal ceramic. That's the YbCO, so we call a high temperature superconductor. Now we're going to push those down a bit just until they cool down. They're still boiling right now, so we're going to give them just a second. It's kind of like cooking a little bit. And I'm going to get this magnet to see what happens. Now, remember, when we saw the electron beam, when we interact electrons with magnetic fields, they react to it. Electricity and magnetism are very strongly linked. Now, normally, when we put a conducting object next to a magnet, the electrons are going to try to cancel out that magnetic field. So, this is actually how electromagnets work. We put in electricity, push it through a current, it creates a magnetic field. If we were to put another conductor in there, it would try to resist that magnetic field by having the electrons travel in the opposite direction. Of course, unfortunately, eventually they run out of energy, they stop conducting. It takes energy for electrons to travel through a material. But in a superconductor, the electrons don't exert any energy when they conduct through the material. So actually, they can resist a magnetic field perfectly. And we can see that happen right here. So I'm going to get my gloves back on because I'm diving into this liquid nitrogen. Our superconducting pucks have now cooled down to liquid nitrogen temperature. And I'm going to, it's always a little tricky with the, take one out, pop it in my gloved hand. And this right here is a large, very powerful magnet. When I put the superconductor on top of that, what's happening there is it's going to resist the magnetic field. And indeed, we see that it's actually just floating on top of that magnet. Right, so I'm going to move it around a little bit. It's resisted the magnetic field and is levitating above the magnet. Now you might be thinking, okay, well, whatever. This is a trick of the camera. But if I turn it upside down, we see that it is actually perfectly resisting that magnetic field. And now that its electrons are moving to resist that magnetic field, it'll stay that way because there's nothing to slow down the electrons. It'll keep resisting that magnetic field. And in this case, that means it's actually going to stay perfectly in the same spot relative to that magnetic field. Okay. So I actually have two magnets on here. I have one that's square. That means that the magnetic field kind of looks like a square, let's say, and one that's circular. The magnetic field kind of looks like a circle. So on the square, we hold the magnet in place, and as I push on it, it doesn't really move very much. All right, I'm going to get myself out of the way just so you can see that it really is levitating on there. Even if I hold it upside down, it's levitating on there. But if I put it on the circle, well, the magnetic field doesn't change as it would twist. So I pop it onto the circular magnet, and indeed, it's still levitating, but it's able to freely spin. So again, let's see. This time, sometimes it does go away. Oh no, we're getting it to work. So this is a quantum effect where the electrons are able to travel freely, allows them to lock into a magnetic field. So there's no current, there's no batteries or anything involved here. This is just the physics of superconductors next to a magnet. We have this levitation and this resistance to go to a different magnetic field. All right, I see that I am running out of time, so I will just quickly switch back to the slides for the wrap up. So this is actually something we call the Meissner effect. When we go even colder, we go to negative 273 degrees Celsius. That's near absolute zero. That's where superconducting quantum bits used in quantum computers work. If we go even colder to microkelvin or nanokelvin, that's where we can actually look at trapping individual atoms and keeping them in the same place. So all of this is very, very important for the field that I work in. It's called quantum information science. So I'm a physicist by training. I love physics, but quantum science is much bigger than physics now. It is a mix of computer science, mathematics, cryptography, chemistry, physics, engineering, and even more. And when we start applying these ideas to things like computing, communications, sensors, materials, or foundations, really looking at what makes quantum mechanics work, how all these weird ideas come together into something that makes sense. We need people with many different interests and many different backgrounds to work in this field. So if you're not into physics, I'm sad, but I understand. But if you're really into computer science, there's a lot of neat ways to get involved with algorithms on quantum computers, mathematics and cryptography, new kinds of communication protocols, chemistry, engineering, new kinds of sensors and materials. Lots of interesting ways to work in quantum physics. So I work at the Institute for Quantum Computing at the University of Waterloo. We have over 150 graduate students and over 30 independent research groups working in this field in multiple buildings at the University of Waterloo from many different departments. Give us a follow and check out our website if you'd like to learn more about that. And with that, I would like to thank you all so much for joining me today. I'd like to thank Jesse so much for putting this together. And I'm more than happy to answer any questions.
Fantastic. Well, John, thank you so much for diving in with that. The levitation thing is wild. I've got to tell you, that's one of the freakiest, weirdest things I've ever seen. And I mean, you've done programs with this before. We've never had the Meissner effect featured. That is like, I mean, you explained it to me, so I do understand in the bear thing. But you are quite the clever man. Now, you did mention we are a little longer than usual, so our classes have had to go to other periods, and that's totally fine. But I do want to wrap up with a few quick questions before we end the broadcast today. So you mentioned repeatedly iqc.ca. Like if people want to learn about your institute, get involved, learn about the work that you do, that is the one-stop shop. Are there other resources? So if our kids are getting into this in middle school, high school, are there books or websites or anything you'd recommend that maybe inspired you or that you know really impact people in a meaningful way?
Absolutely. So if you're really into computer programming, there are a ton of resources about quantum computing in particular right now. Lots of different programming languages that are open source. I'm hesitant to name any particular one, but if you Google quantum computing, you'll find some. So if you're into programming, that's a good way to get involved. Uh, if you're into books in particular, it depends on what angle you're into it. I always recommend the book How the Hippies Saved Physics. If you are into it from a philosophy and history perspective, it's a really interesting story about how um, kind of free thinking hippies found new ways to explore quantum mechanics and how some of the far out ideas actually resulted in some very interesting changes in science. So that's by David Kaiser. I highly recommend that one. If you're interested in more of the physics side, how to teach physics to your dog by Chad Orzel is a great one, getting at some of these fundamental concepts such as wave particle duality. And if you're just interested in physics as a whole, I mean, when I was in high school, the quantum field wasn't quite as huge as it is today, especially the quantum information field. And I got really inspired by Stephen Hawking's A Brief History of Time, which does touch on quantum mechanics as well as general relativity, space science. If you're interested in science and you're looking for a book to read, that is absolutely a classic.
Fantastic. I read Brief History of Time when I was about the age of some of our older kids today. It really is an amazing read. I know when he created it, one of the things that they told him as a publisher was like every time you add an equation, you'll half your sales. And I think it's still sold like 10 million copies or more. Like it's one of the most popular science books of all time. So I do encourage you. I actually have an extra plug. It is on my shelf behind me. A Short History of Nearly Everything is general science of all kinds, written by a non-scientist, but it does dive into quantum a little bit. It's a really, really fantastic book by Bill Bryson. So that's your extra plug from the non-quantum physicist today. John, I mean, I guess one last note for our classes today. Is there we highlighted resources, we highlighted the amazing work that you guys do. If people want to become you, Are there courses in school that they should take? Is there anything that really jumps out that, okay, you've got to do this at this stage to end up in a position like you where you get to do this for a living?
Yeah, it's a good question. I think it really comes down to what angle you're looking at getting into it from. So myself, I'm an experimental physicist. So some of the skills for that is obviously you want to make sure you're taking your physics classes at the highest level you can. You're going to need mathematics. Uh, a lot of people look at like calculus is definitely one that you need, linear algebra, vectors, and matrices, taking that discrete mathematics when you get into high school, grade 11 or 12. Um, I also always recommend looking at coding. You don't need to be an expert coder necessarily to get involved in the sciences, but every science you get into is going to need at least a little bit of coding. So knowing the basics is important. But of course, like that's the route that I took, and that's because I like working on experiments. If you really want to get into the theory, then you need to focus more heavily on the mathematics. If you want to get into it from the engineering, you can let some of the mathematics slide early on and really focus on the hands-on shop work.
Yeah,
Computer science, forget about the physics entirely almost for the first bit and just really focus on algorithmic design. Chemistry is of course important as well, and if you want to get in some of the sensors, biology is important. So it really, like, essentially whatever your interests are, take whatever courses interest you. If you're
yeah.
interested in quantum, you will find a way to make it work with your interests as long as they're vaguely scientific.
Yeah. Fantastic. I mean, it's a good sort of broad overview of the sciences that get you into that field. I do like that you emphasize coding. So Canadian classes, we've got a bunch of
Mhm.
Canadians of course today. Kids Code, Jeunesse, and Canada Learning Code are classically like the two biggest, fantastic organizations run workshops all across the country. So if you want to get your first start in to end up like John and make things levitate with magic, I mean science, then that is your good way to go about that. Well, thank you so much for joining us for World Quantum Day celebrations and highlighting this to all our students today. John, this has been fantastic. And again, I encourage all our groups, check out iqc.ca if you want to learn more, get involved, get excited. Maybe not quite as much as John. Very few people are as passionate as you are. But I hope you all take the chance to do that. And for now, we'll wrap up the broadcast. Have a wonderful day, John, and see you later. Bye for now.